So on this topic, we're going to cover the antenna radiation impedance. And as we've done pretty much with everything else in this course, I'm going to discuss radiation impedance from a system perspective, meaning from looking at the antenna as a device. So the main idea that we have here is that we always have some type of a generator, which here I will schematically show as VG with some type of an impedance ZG. And this generator is going to feed an antenna, usually through a transmission line, which here I will call TL. And this antenna is going to take the power that is incident to it, and it will try to radiate it. So there will be some incident power. In general, there will be some reflected power, and the antenna will basically take the rest. So as far as the system is concerned, as far as the source is concerned, essentially the antenna appears just as another impedance, because it doesn't actually matter what the antenna does with this power, the source simply won't see it back. So if I call ZA the antenna of the impedance, in general that will be some real part and some imaginary part. So there will be some type of a reactance that the antenna will have, and we will see a couple of examples on this. And then there will be some real part which is actually related to the real power consumed, and I put the consumed in quotes, by this antenna. Now, how does this antenna consume power? It may actually radiate it. So there is some part of the real part that we will call the radiation resistance. And then there's going to be some part that will be lost, which I will call the loss resistance. So by writing essentially the radiation impedance in this fashion, we can essentially say that part of the power that will go to the antenna will actually be radiated. So we're going to call the P radiated as 1/2 the current in the antenna square times R radiation. And some of the power will actually be lost. So the lost power will be given as 1/2 I of the antenna gain square times R loss. So it's actually this first equation that you will see here that basically forms the definition of the radiation resistance. So in other words, the radiation resistance is essentially a fictitious resistance that would have consumed the same amount of power that the antenna is radiating. So the radiation resistance has actually units that are definitely ohms. And most people, when they talk about the radiation resistance, they calculate it exactly by this equation that you will see here. Similarly, the effective losses of the antenna that are related to the efficiency we were discussing in a previous lecture are essentially given by this equation here. So if I basically count the amount of power that is being lost, I can define effectively a resistance that would have consumed the same amount of power. That's the loss resistance. That resistance could represent true ohmic loss. For example, it could represent the loss of the wire if it's a thin dipole antenna. Or it could represent dielectric losses if the antenna actually has any dielectrics. So, and then the final loss of power is clearly that reflected power, which we can avoid, or at least we can try to minimize, by inserting a matching network between the transmission line and the antenna. So normally people will go ahead and insert a matching network right here to essentially minimize the power reflected by this antenna. So essentially, out of my incident power or my input power to the antenna, I have two potential losses, the reflected power and the lost ohmic power, and then I have one useful power that I'm basically trying to maximize. So based on that, I can also define the efficiency of an antenna, which we defined before. So the efficiency eta is actually nothing else but the power that is actually being radiated over the power that's being radiated and the power that is being lost. And sometimes people will also insert the power that's being reflected in the sense that this is not really radiated. So most of the times, though, that reflected power will try to make it as small as possible if that is something we can actually do. Now, radiation resistance, I'll give you some examples. So for example, a half wavelength dipole, which we will see in a little bit, the radiation resistance is something in the order of 70 ohms or so. It depends on variable different things. But in general, the closer this number is to 50 ohms, which is our reference impedance in most systems, the better we actually are, in the sense that the matching network can be made quite nice. Also, this XA, which is essentially the reactance of the antenna, can be positive or negative. The antenna may have a capacitive behavior or inductive behavior. It can also be a small or a large number. Let me give you a couple of examples related to this. So this is a typical radiation impedance of a resonant antenna, and specifically for a dipole antenna. So what is actually interesting to see here is that there are two plots here. There is basically the real part, which is this guy here, and then there is the imaginary part. And most antennas that are of the resonant type will basically zero out the reactance right at resonance. So essentially, you can see that for a half wavelength dipole, you basically have a zero reactance roughly at about half wavelength. And then you can calculate the radiation resistance at that point. And that will be essentially the radiation that you have to match with a matching network when you design this antenna. Now, what is also interesting to notice about a resonant antenna like the dipole is that away from resonance, the radiation reactance, rather the reactance of the antenna, actually changes dramatically. That's a direct consequence, of course, of this being a resonant antenna, meaning it works well only at its design frequency. And away from it, it actually develops a very high value of reactance, which means it becomes very, very difficult to match those antennas. In fact, resonant antennas in general are called also high Q antennas, in the sense that the resonant circuit that represents this antenna is a high Q structure. And that in general is bad because it's a very difficult antenna to match in real life scenarios. There are also broadband antennas, and this is an example of a log periodic broadband antenna. If you notice this figure, this is basically a collection of dipoles that have been carefully designed to radiate at different frequencies. For example, you will see short dipoles here to essentially radiate the high frequencies, and you'll see longer dipoles here to radiate the lower frequencies. And there's a specific design behind the log periodic antenna, which we won't cover in this class, of exactly how you achieve that. But the point is that if you can afford to do something like this, you can get a very, very broadband behavior. And here's an example where the manufacturer is giving you the VSWR. Remember, this is the standing wave ratio related to the gamma, the reflection coefficient. The ideal value is 1, but essentially anything below 2 is pretty good. And you can see here that this antenna maintains a VSWR of below 2 for well over a decade, basically from roughly 160 megahertz all the way to almost 3,000. And so in a typical broadband antenna, you can get behavior like this, but of course the cost is the complexity, right? So the antenna is typically larger. Broadband antennas tend to be much larger. They tend to be much more complicated to design. And the other interesting feature about the broadband antenna is not just how well matched it is, but also how good of a gain it has versus frequency. So if you look at the data sheets, and I looked at the data sheets of this particular antenna, they will also give you the gain of the antenna in dBi, as we discussed before. And what is interesting to notice here is that the gain, of course, does vary, but it varies around a middle value of maybe 9.5 dBs, somewhere here, plus or minus maybe 1 dB or so. And so in a broadband sense, in a broadband antenna, it's not just good enough to match the antenna, but it's also good enough to, it's actually essential to maintain its main radiation properties. Gain is one example over the required bandwidth. So what I really want you to keep from this is that is essentially what is the radiation resistance is proportional to the radiated power, and the fact that you might have the impedance of the antenna varying very widely versus frequency, like in the case of a dipole, or it may vary very smoothly versus frequency for a broadband antenna.